Welcome to another Sunrise Series video showcasing Use Case 1.2, Connected Perception Testing and the Sunrise Safety Assurance Framework in action. This video showcases an automated driving system, ADS, tested at a signalized urban intersection with an intersection moving assist, IMA system. It validates 4 SAF parts: allocation, execution, coverage, and test evaluation. This demo focuses on ADS responses to traffic lights and V2X supported intersection crossing in scenarios like nominal stops, restart on green, signal delays, and priority/non-priority obstacles, using both virtual MATLAB/Simulink and hybrid OMNIT++ veins, Sumo, real ADS IMA, RSUs/OBUs setups. We build a structured safety argument process focused on scenario coverage, pass/fail evaluation, and a binary safety case. Key artifacts obtained are a final allocation diagram for virtual/hybrid tests, co-simulation framework for risk-based, edge case testing, modular V2X, ADS decoupling, hybrid tests validating simulations. We start with virtual test of ADS model using MATLAB/Simulink. Scenario 111 shows the ADS stops on red light. Scenario 121 shows ADS restarts on green light and passes it. Scenario 134 shows the ADS stops before the red because of the delayed message from IMA. Scenario 211 shows the ADS stops for the priority obstacle vehicle on the right. Scenario 221 shows the ADS stops urgently to allow a non-priority obstacle vehicle on left to pass but collides with it. The simulation requirements are compared with virtual test setup capabilities. MATLAB/Simulink covers road networks, traffic lights, and dynamic agents. AD functions are partially supported to be handled via the XIL framework. V2X communication and perception are not simulated and require direct testing in XIL. Then, the final allocation diagram is obtained. The subject vehicle, its AD functions and dynamics are real. Connectivity and positioning are hybrid. All other elements are simulated. This validated the allocate part of the SAF. We tested scenarios with varying parameters, initial speed, distance to traffic light, deceleration, and ADS jerk. Based on peak jerk linked to unsafe scenarios, 5 critical scenarios were selected for hybrid tests, covering nominal stops, restarts, light failure, and late obstacle appearances. These hybrid cases complement virtual tests, validating scenario coverage SAF.
We will see on this video the execute block of the use case 1.2 dealing with urban AD validation for connected perception testing. This work has been done by VED on our car and on our facilities on our test grounds.
Test evaluation validation. Logged execution data was analyzed to extract KPIs, comparing simulation and hybrid tests. Ego vehicle speeds at trigger points closely matched, with deviations under 2 km per hour, confirming consistent initial conditions. Minor differences were due to real-world factors like track length. Trigger distances were also consistent across scenarios, except in scenario 211, where early triggering in the virtual simulator caused a 3-meter deviation. ADS decision-making evaluation. The ADS makes correct and consistent stop decisions across all scenarios. In case 121, it resumes after the green light as expected. Scenario 211 shows speed reduction from 40 to 30 km per hour. No adjustment is needed in slower cases. A single stop decision per scenario confirms robustness. Real-world decision delays, 27 to 32 milliseconds, remain below the 40 milliseconds control cycle, with no impact on performance. ADS control performance. Control accuracy gaps are due to limited deceleration modeling and earlier obstacle triggers in real tests. Control delay matches design, 40 milliseconds, traffic lights, and 80 milliseconds, intersections, though sunrise results suggest the extra 40 milliseconds may be unnecessary. In scenario 221, a confirmed collision from delayed acceleration was handled safely. Vehicle stopped and activated hazard lights. ADS comfort control. Traffic light scenarios show good alignment, with slight deceleration underestimation in simulation at low speeds, less than 10 km per hour, causing longer stops. Intersection cases show larger gaps. Scenario 211. Earlier obstacle trigger enables gentler braking in real tests. Scenario 221. Sharp braking approximate -6 meters per square second at 20 km per hour reveals the approximate 1 meter per square second gap. Here is a summary of decision-making and comfort KPIs. Decision-making and longitudinal control KPIs are within expected and acceptable ranges, with acceptable control delay. However, longitudinal control accuracy is slightly low, indicated in orange. Comfort KPIs for average acceleration are mostly in the normal to aggressive range. In the non-priority obstacle case, discomfort reaches the urgent range due to the unexpected, priority-violating obstacle appearance. Connectivity results show strong CAM performance. The successful delivery ratio is close to 100%, and the average delivery delay is approximately 140 milliseconds. The evaluation confirms close alignment between simulation and real vehicle behavior, with minor differences due to event timing and low-speed braking. Connectivity delays, 140 ms, affect trigger accuracy, and the simulator slightly underestimates strong braking. While MATLAB supports functional validation, performance tuning is done on real vehicles. Future improvements include faster connectivity, 40 to 80 milliseconds, better low-speed braking models, focus on rapid response scenarios, and streamlining decision steps to reduce reaction delays.